We have just watched this video by John Conway, yet another video that we've watched. John Conway. Yeah, I mean, he mentions some of the things that he did. If you are interested, you can look at this thing, surreal numbers. He published a paper called, I think, All Numbers Big and Small. So he discovered certain numbers that we didn't know that existed, and he did discover it by playing games. Okay, somehow some sort of gameplays correspond to some numbers. Go read about it. There is a very nice book by this guy. Do you know Donald? He is writing this, The Art of Computer Programming. I think it's not finished yet, but that's another person who should you should look for. So he wrote a book about surreal numbers, and he wrote it in 1 week. And there is another number file video where he describes how he wrote that. And okay, let's stop watching videos now and start with Game of Life. Okay, so what is Game of Life? It's a 2D cellular automaton, and we already watched how Conway described that he came up with the rules during the coffee breaks over a span of 18 months. So here are the rules. I will present them in a bit different way, okay? So you can be either dead or alive. So you are either 0 or 1, okay? And what happens to you, so this cell, the middle cell is the main cell right now, and what happens to it depends on how many alive cells it has around it. This thing, this 8 neighborhood, is called Moore's neighborhood, okay? So what can be the sum of those states? Let's call it M. M can be 0, 1, 2, 3, 4, 5, 6, 7, 8, right? M is the sum in the Moore neighborhood, okay? Are you following? So here is the different way that I'm going to present it. I'm going to talk about operators. I will say that if it's 0 or 1, it's decay. If it's above 3, it's decay. All over here, it's decay. And only here, it's growth. And over here, it's stability. Okay? So D is decay. What does decay mean? It means that 0 goes to 0, 1 goes to 1. Okay? So if you have 0 or 1 neighbors around you, you are going to die because of underpopulation. Okay? Stability, S is for stability, is when 0 goes to 0, 1 goes to 0. No, 1 goes to 1. Okay? And growth, G is growth, and it corresponds to 0 going to 1, 1 going to 1. What operator is missing from this game? The difference is that I made an error. Yeah. Thank you very much.
The one operator that goes 0 to 1 and 1 to 0.
What would you call it? Oh, nice, nice. Resurrection, but doesn't work for 1 goes to 0, right? But 1 goes to 0, then 0 goes to 1. Very nice. Resurrection. We called it oscillation, I think. Okay? But in any case, very good. That operator is missing and it's not there. Okay? So, that's the game of life, and we can now code it from this.
Why is it missing?
It's just in the definition that Conway provided, there was no such operator. But notice that we have huge amount of decay, okay, everywhere, just one growth, okay, and stability. So you would expect this to decay away, but it doesn't. It does all these interesting kinds of stuff. So far, so good? So here is a program that runs. Let me just run this program and you will see how it looks like. So I started from random initial conditions. Is it too big of a plot? Maybe I can make it smaller. 6 by 6 maybe. So what you have here is, did you see those, like, okay, it's just running for 100 steps, so let's run it for many steps. I will describe the code, but notice that there is this thing that goes. Do you see it going? And then it's distracted. But in general, you have these themes. You see, like, you have these still lives, you have these oscillators, blinkers, and you can see that it has a theme. It's like there are main characters and etc., that kind of stuff. Some activity going on. And as Conway mentioned, you don't know whether it will stop after one step or not. Look, this one is going there and creating some avalanche there, etc. Right? So people are obsessed with this. Like, there is this thing called LifeWiki, and there's all kinds of tutorials, guns, puffers, oscillators, puffers, spaceship with families, adjustable spaceships. I mean, just let's find one of them. I don't know how that one works. It's too big of a thing. Maybe oscillators. Let's talk about oscillators. Let me go to just the Wikipedia page. So, for example, this one is actually resolving one problem. Can you create an automaton that just expands indefinitely? And this was the answer. I think there was a few dollars prize for it, and the guy won it. And this is just creating Gosper's glider gun. It's creating these gliders, and it goes on forever. But these turn out to be very useful things when in the description of Conway's game of life being Turing complete. Because once you have all those things that are created, then you can make them interact with each other and create logic out of it, right? So you see Wikipedia page is better. Spaceships, for example, glider is the most common one. And then there are these lightweight spaceships, middleweight spaceships, heavyweight spaceships. There's a pulsar of period 3. There's this pentadecathlon that goes for 15 periods. These you have seen in the game of life, right? So it's interesting in many different ways. Let me talk about the code. You can see that all the rules are implemented in just one line. Okay? But let me explain the line that comes before that. Do you know what this one is doing? So let me tell you what that one is doing. Do you know what convolution is? No. Okay. Let me tell you. So let me tell you first what this line is doing. This line is taking the state matrix A, right now zeros and ones, n by n matrix, and it's convolving it with this 3 by 3 matrix, 1, 1, 1, 1, 1, 1 everywhere except for 0 in the middle. Convolution is this. Let me explain. So I have, let's say, a matrix etc., right? And I have the convolution window 1, 1, 1, 1, 1, 1, 1, 1, 0. It's very important nowadays with convolutional neural networks, like deep convolutional neural networks. Very important. Why? Because, for example, do you want an edge detection? You just write something like this, and you get an edge detection in x direction. Let me tell you how it works. Let's talk about this one. I put it over here. Okay. What it does is you multiply 1 by 1, 1 by 1, 1 by 1, by 1, by 1, by 1, by 1, by 1, by 0. And then sum the whole thing up and write it in the middle cell. That's exactly what Game of Life is doing, right? So to decide what is going to happen in this cell, we are wondering what's the sum around it. Okay? Why we are using convolution? Because since it's a very useful operation for other purposes, convolution algorithms are really fast. So basically, when I convolve this with that, it just scans the whole matrix and writes the sums around it in the middle. Good? So I have the sum for each cell, the neighborhood sum. Then what do? Okay. I have to describe you something else. So let me write from these operators. Let me write delta S. Okay? If this is the state S, what happened over here with delta S? So I'm going to write this delta S for decay as minus S. Would you agree with that? I'm saying that delta S is minus S because if it's 0, minus 0 is 0, and change is 0, so it's 0. If it's 1, delta S is minus 1, so the change should be minus 1, and it goes to 0. Yes? Delta S is minus S for decay. Let me write it with color code, minus S. What is delta S for stability? 0. Very good. So for stability, it is 0. What is delta S for growth? If it's S, then 0 goes to 0. Right? So it's 1 minus S. You can write it in many different ways, but 1 minus S leads to very nice things later on. Okay, 1 minus S is good. Do you understand it? Delta S? You didn't understand 1 minus S. Okay, very good. So this is S, right? This is S, the state. So 1 minus S, if S is 0, 1 minus S is 1, which means that the change is 1, which means that 0 goes to 1. If the state is 1, 1 minus 1 is 0, so the change is 0, so 1 goes to 1. Good? Very good. Okay. So, look at here. Do you know what this means, by the way? It just adds to A, right? Like this one corresponds to this one, right? Okay. So then it's delta S, right? Or delta A. So look, if B is 3, which means that if the neighborhood sum is 3, then we use growth, right? If B is less than 2 or higher than 3, so less than 2 or greater than 3, then we have decay, minus A, right? Why don't we have stability? Because delta S is 0 anyways. So that's how the code works, okay? What can I tell you more about game of life? It's just interesting. Okay. For example, let me just look if I have some presentation slides for game of life. We have already watched Life in Life. You don't want to watch it again, right? Or, You weren't here? I think this one also has music, so we can watch it one more time. So as you can see, these spaceships are there, the larger ones, the smaller ones. Yes. Okay. What do we see here? I mean, these stuff are not. Do you see these proteins taking something? It's like biology, and some transitions are happening here. There will be a transition soon. So it's actually calculating where it is. But do you see that thing that goes around? So they were there for a reason. They were calculating when to do that loop. Do you see now? It's changing the state, and you are creating game of life with game of life. Because it's Turing complete, you can create anything with game of life. Okay. So it also captured the interest of physicists or mathematicians or people in between. For example, Perbach, we mentioned Perbach's paper about criticality of game of life. Do you remember? So what he did is he disturbed the game of life system many times, just like he did with the sand pile system. He takes a game of life system and he disturbs one cell and sees how much time it takes for it to settle down, and that corresponds to avalanche. And then when you plot the avalanches in log-log scale, they come out linear. So he says game of life is critical. Okay? Okay. So far, so good. Now I will start talking to you about our study on it. Okay, we made a study, and that study is part of your homework. So let me describe it in detail. So we just were motivated that maybe we can also write something about this system, but we modified it so that it could be maybe more interesting. Here is how we modify it. Do you remember delta minus delta S, 0, 1 minus S? That's Conway's game of life. We just put lambda in front of it.
Lambda S can never be S, right?
What?
Lambda S cannot be S.
What is lambda? I didn't describe lambda yet.
Delta, sorry, not lambda.
Delta S
Yes.
cannot be S.
Yes.
Why not? If delta S is S, then 0 goes to 0 and 1 goes to 2. So in this context, no, it can't be S. You are right. Okay? Come on. So this is Conway's game of life. This is something that we call logistic game of life. And you will understand later on why we call it logistic in the next chapter. Okay? Now, Conway's game of life takes 1 to 0, 0 to 1 when you have growth and decay, and stability just remains. But depending on what you choose lambda, it takes it to other places. In fact, you can even now see the fractal nature here. You see, let's say, by the way, in Conway's game of life, you can only have zeros and ones, right? Only allowed 2 states. In logistic game of life, you can have any number between 0 and 1, okay? So let's start with uniform distribution. Decay would squeeze this distribution down here, okay? Growth will take it up here, and stability will just remain like this, right? That's one iteration. What if you take the second iteration? You take this one and just squeeze it down here. Are you following? Or this one and squeeze it up here, and stability remains in between. So it goes into this. It's like fractals. It's like Cantor set. Do you remember Cantor set? You see, in this TV series, that is this lecture, there are these characters that appear in one episode, and you shouldn't forget about them, okay? Because they will reappear somewhere else. So here's the thing. Behind my pretty face is standing 1. Okay, there's 1 here. I can show you. Oh, there you go. 1. If you do decay, 1 goes down to 1 minus lambda. Okay? If you do growth on 0, it goes to lambda. Okay? If you do stability, 0 goes to 0, 1 goes to 1. Now, in the second order, so you started with 1 and you operated on 1 by d, right? So this is d1. d1 is 1 minus lambda, right? Okay, maybe you should see what this game can do, and first you need to be impressed by it. Then I go into details. So let me start with the original game of life here. This is game of life, right? Lambda is 1, and you have game of life here. Let me take lambda down. Already started being colorful. I can always reset it, don't worry. I'm taking lambda down, 88, 87, and it's much more populated now. So I'm going down, down, down. All these kinds of different stages. And there are 3 things that are trying to gain territory. There is this zeros that were there before. Zeros are the dark places. Then there are these blinkers. You can see something is blinking in the background. And then there are stripes. If I go down further, you will see stripes more and more. Do you see them? And if you continue going down, stripes win, and basically the activity is present only in between stripes. Do you want to see it more closer maybe? So let me just interrupt it, and I'm going to do the following. I'm going to take this to 6. Don't worry about it. Okay, I can always restart. I can always go down in lambda. Is this fun? This is fun. Okay, going down you can see stripes win, and if you go down enough they just stay there, and there are these things that are living on top of it. Okay? Okay. Back to Conway's game of life. Let's increase lambda. If you increase lambda, I can always restart, don't worry. It dies out, but I can always resurrect them. Especially after 125, it becomes, you may think that I wrote a game of like arcade game where there's this ships that I actually designed. No, it's just appearing because of the rules of the game. And if you continue increasing lambda, there are all these kinds of different behavior present here. I'm increasing lambda. It's do you see the ships that appear?
Why colors change?
Hmm? What?
What makes the color change though?
The colors are the colors are changed. Do you see like there are these fish going around? The colors are changing because we no longer have zeros and ones. We have all kinds of different numbers, different values.
It's like a
Oh,
scale between 0 and 1.
I was not doing anything and it started a replicator. Did you see that? Let's see it again. Do you see those replicators that replicate? Did you get your answer? Yes, I'm changing lambda now, and it becomes this thing. No. You are going to die in 7 days because you watched this, right? You have seen the ultimate truth, so. Yeah, okay. Like, if you go to 1.75, it's this weird fungus kind of thing. It's like, you are joking, but we are serious about it. Yeah. We are trying to actually measure the same kind of parameters, just like in Isaac model you see some order parameters. We are doing the same for this one. We did the same thing for this one, and now we can go back to being serious about it, right? So every time you operate on the system with decay or growth, you go to a higher order of lambda. Okay, this order, first order is a polynomial in the order of 1 in lambda. Then there is second order lambda, third order lambda, etc. And we have already seen this. So here's the thing about game of life. Although Conway says that you will not know what will happen, if you start from random initial condition, it usually dies out in 10,000 steps. Okay? That's another thing that we wanted to rescue. Most of these papers, not this one, most of these papers are questioning whether game of life is critical or not, whether it will remain flickering while not being too chaotic, etc. Well, my answer to that is no, it's subcritical. It's very close to criticality, but it's below criticality. criticality, okay? So it dies out. It's more on the order side. There are just too many zeros in it. But you can revive it, or our word for today, resurrect it, by taking lambda below this 0.875. We just looked at, this is, by the way, your homework, just to reproduce this image, okay? We tuned lambda down and we saw that suddenly it starts to be active. Let me show you what I mean. If you are 10 to the minus 10 above 0.875, okay, 10 to the minus 10, the activity decays in 10,000 steps. No, 100,000 steps? 100,000 steps, according to this figure, right? But it's consistently down in 100,000 steps, right? But the other one keeps running after 1,000,000 steps. Do you see it? So something fundamentally different is happening at these critical points. And we tried to understand it. Do you want me to explain? I can explain it. Why not? Here's the explanation. What is 0.875? It is, I didn't mention one thing. I go back and forth, but it's okay, I guess. Here's one thing that I forgot to mention, and I always forget to mention this. Once you are in logistic game of life, you no longer have just zeros and ones. You can have any numbers. So m actually can be any number between 0 and 8, right? So to put it, to make the system fairly similar, we put some parameters here. We put T1 equals to 1.5, T2 equals to 2.5, T3 equals to 3.5. These are just separators, and if you are over here, you are in decay. If you are over here in stability region, if you are here in growth. So it's exactly the same idea, just you just are now working with continuous numbers, or you are working with a Cantor set. Did you follow this? So that's why it matters whether you are above T1 or below T1. So why we have a critical transition here? Because let's say you have this kind of a state. What is the sum of these cells? It's 4 lambda, right? If 4 lambda is equal to T3, 4 lambda equals to T3. Let's say it's above T3, then you are in decay region. If 4 lambda is below T3, then you are in the growth region. So suddenly, this particular state, normally it would go to decay, now it goes to growth. That's why you get closer to critical point. Does it make sense? It was subcritical just a little bit. Now it's critical. So that 4 lambda equals to T3 made it possible to go to the other side. 4 lambda is equal to 3.5. 3.5 over 4 is 0.875. Good? Then we realize that there are many other transitions. For example, there is a transition here. Let me just put it here. There is a transition over here that is quite intriguing. And we can explain all these transitions. This is the density. So the density comes up until this point where 3 lambda is T2, suddenly increases. Then there is another sudden decrease here. And we can explain all this by Cantor set going from one stage to the other stage. These are too many details. And if you have any questions, I can answer, but otherwise, we can have a break. Do you have any questions?
What is density?
Density is average of the whole states.
All states.
All states, like
First zero.
why it is 0 over here. It's not really 0. As you can see, 0 is here, and when you have Conway's game of life, I think it's around 0.025, okay, which is in milli-electron volt, corresponds to room temperature. Has nothing to do with the other thing. Do you have any other questions? Did you get your answer? Yes? Because it's a lot of zeros, then a few ones that remain after it settles down. So those sum up to, on the average, 0.025. But once you tune it, you can go to higher values. Okay, we can have a break now.
How are we calculating the average? So we are like adding just the lambda values of every side and dividing it by the number of sides.
Not the lambda values, S value, like the state values. Like, yeah. So what is the state value here? What is the state value here? Total divided by...
From 0 to 1 between. They are between 0 to 1.
Yeah.
So we are adding everything and just dividing by n.
Yeah. Yeah, exactly. We are adding everything and dividing by n squared. I repeated it so that it's in the recording because it's useful for the homework. Okay. Thank you very much.